We're going to do a brief overview of the magnetic properties of matter. Most of the ideas that are introduced in this section actually require very advanced physics to delve into them in much detail. So this is really only an overview and hopefully will allow you to understand some of the things that you know about magnets, but we're not really going to go into details. You're rarely going to see them on calculations. So the first thing to realize is that we need to jump down to the atomic level to think about for instance, how a permanent magnet works. Now, there's two models we can think about. The first is a classical atom, where this would be, for instance, your planetary model of the atom. We have an electron that's orbiting the nucleus. So you can think of this as having a magnetic moment because you have an electron going in circles. A charge traveling is kind of like a current, and so this is one argument that you can think of individual atoms as having magnetic moments because there's a little electron going in circles. Now, you probably know that the planetary model of the atom isn't true, has a lot of problems, doesn't work. So, depending on what you need to do, it might be okay to use it. Like simply you can think about the fact that atoms can have a magnetic moment, and once you put a bunch of magnetic moments together, you have magnetic properties. Okay, cool, you have a permanent magnet. So that works. But if the planetary model of the atom bothers you, as it should, we can then switch to a quantum perspective. Now, we're not going to say much more about this. If you want to learn a lot more about this, you should be a physics major and take quantum mechanics, where we cover this in actually great detail. The idea is that there's a property of individual electrons called spin. So this isn't an atom now, this is a single electron. And our little electron has this property called spin, which is an intrinsic magnetic moment. So every electron has its little magnetic moment. And then when you have atoms, the magnetic moments can interact, and so you might have zero magnetic moment of the total atom, but in many atoms you're going to have some magnetic moment if you have unpaired electrons, things like that. So you might have heard the idea of spin up and spin down, for instance, with chemistry and electron levels. So that's what we're talking about here. Spin is a misleading name. It isn't that the electron itself is rotating. The electron, from a quantum mechanical point of view, is not a little sphere. We talk about it in this class as a point charge, meaning that it has no size. Physics has never found a size of the electron. We can get all quantum mechanically and call it, a wave, a matter wave. But otherwise, it's a point. It's discrete. It has no size. So this is fundamentally quantum mechanics. If you want to learn more about it, you have to take quantum mechanics because there is no way to explain it briefly. In fact, you kind of need a PhD to really start to be like, oh yeah, electron spin, that's easy. So again, this is easier to understand but wrong. This seems to be true but really requires a lot more physics to understand. The takeaway is that an atom has a magnetic moment. So what can we do with that? So let's think about two cases. We have a normal solid, so most materials, you have all of these little atomic magnetic moments that are just arranged however. Now what that means is that there's no net magnetic moment, right? They kind of cancel each other out. On the other hand, if you have a ferromagnetic solid or ferromagnet, so a material we would call ferromagnetic, in this case they align. Those little magnetic moments in the atoms align, and now you're starting to get something that looks like a magnet. You have a north and you have a south, and that's like having a bunch of little tiny loops of current that all are creating magnetic fields that are actually adding up rather than canceling each other out. So that's the idea of a ferromagnetic material. It has these atomic magnetic moments and they align. Now, I've pointed out that this is ideal because this is actually something you would see in a permanent magnet, but most ferromagnetic materials are not going to look like this. So when you're handed a refrigerator magnet, it does this. If I hand you a really strong magnet, this is what's happening. But if you just have like an iron nail, that isn't quite what it looks like. What you actually have are what's called domains. And in the domains, the atoms are lined up with one another, but they're not necessarily lined up from one to the next. And so on the whole, it cancels, but we have the ability to actually start rotating the domains, or rotating the atoms within the domain, or actually making some of the domains be bigger than others. So that's what happens when you put a nail near a magnet. We actually do something that looks a lot like polarization, and all we're doing is torquing the magnetic moment. So remember that if you put a loop, so a little magnetic dipole, in a non-uniform magnetic field, or a uniform magnetic field, it's going to rotate. So in this case, we are going to see that all of our little atomic magnetic moments align with the field. And again, in a case of a real ferromagnetic solid, you don't get that perfectly, but you get some domains starting to grow, and so you do at least get some effect. Now, once that happens, you now have a north and a south, so you have attraction. This is also why, if for instance you pick up one paper clip, that paper clip might be able to pick up another paper clip, because you've basically taken this random material, made it look more aligned so that it's become a little bit of a magnet itself. Again, it's not perfect, and so that's why that paper clip doesn't stay a magnet, or why it's not as strong as your original magnet, but that's basically the idea. So that's how permanent magnets work, at least at the level that we can discuss in this class. But if you only have one takeaway, it's that really at the atomic level, there are magnetic moments, and that isn't just in ferromagnetic materials, that's in all materials, which is where, for instance, we can make things like MRI work. So the imaging that we can do, that we talk about MRI scanners a lot in here because it's a cool application of solenoids, that works because just the water in our body even has these little magnetic moments. And you can image this. We can use this to really understand a person's health and what's happening in their body. So again, not a very quantitative section, really just conceptual, but my hope is this will help connect some of the ideas we've been talking about in here with just the magnets that you perhaps played with when you were 8 years old.